I think it's afternoon now, so good afternoon, and annyeong shimnika. And thank you for inviting me to your conference. My name is Martin Chizek. I'm an engineering fellow with Lockheed Martin. I'm also an attorney, so I try to bring a legal aspect as well as an engineering aspect to system safety and software safety. So I appreciate that the previous discussions were excellent, and I think this talk will leverage off those and be complementary to those. And particularly Dr. Reed's, it reminded me that about 2 years ago, the president of Ford Motor Company said by the year 2021, he told his vice presidents, by the year 2021, I want to have a fleet of autonomous vehicles on the road, a fleet of Ford vehicles. And so his vice presidents went off. They bought a number of artificial intelligence companies. They employed consultants. And about a year ago, I was in Detroit at Ford as one of those consultants. And their engineering managers, who are the ones who are going to have to implement this, they said, there's simply no way we're going to have a fleet of autonomous vehicles by 2021. They understood. And why is this? I mean, they're absolutely right. And the reason is not so much the complexity or the technical challenge of autonomy, although it is very technically challenging. The reason is there is no current way to verify and validate autonomous systems to the level necessary to meet regulatory requirements or the independent parties that would have to assess this. Just to go back our engineering basics a little bit, verification is the process of providing objective evidence that your system, your hardware, your software meets requirements, or as they say, did we build the system right? Validation is the same thing, but do we have evidence that we met our users' needs? In other words, did we build the right system? So that's verification and validation, and the reason that is so difficult for autonomous vehicles is several. First of all, it's very complex. They're very complex software systems, and they are meant or going to be, they're intended to operate in undefined environments, whether it's undersea, whether it's the roads that we just saw some examples of, very undefined environments. The requirements still have to be verified and validated to instill trust in, again, trust in the regulators, in the public, in the users of these autonomous vehicles. And right now, there really is no current process that meets all the users or all the needs of this. And reasons are, first of all, requirements, which Dr. Thomas talked about. It's difficult to derive requirements for extremely complex, non-deterministic systems that you cannot predict. There's also a near infinite state space of possible environments and the possible reactions, as we saw in this last video, the possible responses with all the possible environments. There's just an unlimited number of combinatorials you're talking about. And then to add on to that is if we go up to the machine learning, the highest level of autonomy, we can never tell what the system is going to, we can't predict the system if it's learning. Those are all just basic facts. So to get in a little more detail on the autonomy, the particular challenges, first I said was incomplete or vague autonomy requirements. And again, the combination of driving conditions and decisions are too numerous to do classic requirements generation of. And it's difficult enough with a very complex software system to do requirements, and let alone, again, with non-deterministic and adaptive systems. And then, in addition to that, and you'll see on the bottom, is your classic systems engineering V model with requirements on the top left, development along that left leg, and then source code and test and verification on the right leg. Well, if you notice on the very top, the very first step is requirements specification. And again, so in classic V model systems engineering, your requirements are developed first. But again, for autonomous systems, we cannot develop all the requirements, or we can't know all the requirements we're going to need. The next is system complexity and state space explosion. And again, the complexity of autonomous software makes it almost impossible to do 100% testing. The state space explosion refers to the fact, again, that of all the possible permutations and combinations of systems interacting with each other in all these environments, again, you just cannot test all these combinations. And then again, with complex adaptive systems, they can't be predicted, so therefore you can't test everything. And then finally, emergent behavior, and this was referred to in the previous presentations, that when you get all these autonomous subsystems operating together, and then you add on a human element in some cases, you can get unintended behavior. The system will actually do things you would never have predicted it to be. And again, as I mentioned, because it's anticipated to learn over time and react, you could conceivably test today input A plus input B equals output C, and tomorrow it may learn, and now inputs A and B equals output D. So it's extremely difficult to bound this problem. And then this part basically is just culmination of the previous ones, which is trust and certification. And that's really where we at Lockheed are trying to get an aspect of trust and certification for our customers, which are mostly FAA and military. The military has said that, they've quoted, without trust, autonomous systems will not be adopted except where, say, there are things that our pilots can't perform. Unless we can trust in this autonomous system, we're not going to use it. And that makes perfect sense. Civil aviation, the same way. Trust has been identified as a major impediment to introducing autonomy into called the National NAS, National Airspace System. And you know, we know already with autonomous systems are usually safety critical because their failure will most often or can often directly relate to human injury or loss of life, that they have to be certified. And certification even gets more difficult in the aviation arena, where you have human operators interfacing with, for example, a UAV, unmanned aerospace vehicle, where you have to certify now the total combination of the pilot and the autonomy, more or less autonomy depending on the pilot. The way it's done now is essentially you certify your system and you have a certified pilot who's gone through all the training. So you have those two areas. Now as the autonomy takes over the pilot functions more and more, how do you address this interaction where now how do you certify the system for being a good pilot? It's, again, it's a challenge. When we get to automobiles, it's been mentioned slightly, the level autonomy, there are different definitions for levels of autonomy. One of them, and the most popular one, would be the SAE levels. And there's an illustration down there. SAE levels 0 through 5, 0 being no automation, 5 being full automation. And there's a continuum through that, and you'll notice the two right under 4 and 5, the assumption is that there is no operator any longer. In the first 4, well, 0 obviously, but also up to 3 conditional automation, the driver in an automobile is expected to be available to take over functions if necessary. And of course, we're running into the fact, one of the Tesla factors was, I believe the driver was not paying attention. They get bored over time, it's human nature. And so as we get into automation and full automation, again, the challenges to that certification of those systems becomes greater. And then this just kind of reiterates what I was saying. So SA Level 3 expects human drivers to monitor for failure and take over responsibilities. 4 and 5 take the operator out of the loop. And what's interesting here now, so now the autonomous system has to address any situation that arises that the driver might, but it also has to realize if it can't address a situation. What happens when it comes up to a situation it has never seen before? What does it do? There are certainly fail-safe operational concepts within system safety, but automotive recognizes that fail-safe doesn't work in every eventuality. If you're driving across the Dunbarton Bridge in the Bay Area of Silicon Valley and you have a malfunction right in the middle of the bridge, you don't just want to come to a halt because you're probably going to get crashed into and killed. So they want to have a limp home mode where you will continue to drive, get off the bridge, and then to a safe spot, and then go to a safe state, which would be pulling over. But again, much more difficult than your normal autonomous, much more challenging than your normal software complex system. In aviation, they have a little bit different issues. And again, the FAA's problem, as they stated, is how do we assure that an autonomous system that can modify its behavior and that can change over time, how do we, the FAA, certify this to be safe for the airspace? That's their job, right? And the government is traditionally, understandably, very conservative about this. They don't want to make a mistake that results in a fatality, an accident. And even though the automotive companies are being pushed to allow these, their natural reaction is to be very conservative. FAA, they understand there's a lack of trust right now in autonomy by users, by the public, by regulators, and for good reason. We see videos like that, and everybody who sees those videos has the same reaction, which is, you can't trust these autonomous systems. And I can't say they're entirely wrong. So the FAA is cautious about certifying these systems, but they know they're going to have to meet the same V&V requirements eventually that manned systems are, that current systems are. So what is a trusted autonomous system? Department of Defense has said that the decision to deploy autonomous systems requires trust that they will perform effectively in their intended environment, and they won't have any what they call high regret unintended consequences, which means an accident where people get killed. So essentially they're saying they have to be high reliability, excellent performance, and they can't be unsafe. They cannot have catastrophic incidents. So one of the things we've looked at is how do you define, what are the elements of a, quote, trusted system? And we've come up with a number of factors. The first would be system certification or an equivalent. Obviously, that's the current method. If you can certify a system, then it can be trusted. System integrity, we have areas, safety integrity levels. FAA has design, not design assurance, there's a different, design assurance levels basically. And then in software safety, we have levels of rigor. Then there are system dependability. These are classic computer system or IT type dependability criteria. It has to be safe, reliable, reliability and availability are two reliability measures. And then, of course, cybersecurity, that's been mentioned. And then finally, system assurance, design time assurance and runtime assurance, and we'll talk about those a little bit. So system integrity, we have, there's been discussed a little bit, the original IEC 61508 sets out system integrity levels according to an allowable or tolerable failure rate. 26262 is the automotive version of of 61508, and it adds a concept of vehicle controllability. Again, how much can the operator aid in keeping us safe? And again, as we go to the high integrity, or I should say the high automotive levels, the operator is no longer involved in that. Software assurance, all the standards, the different standards for software assurance talk about levels of rigor depending upon your risk level. We all know software, quote, doesn't fail, at least in a classic way. It's the requirements are wrong, or there may be flaws in coding, things like that, but it doesn't fail, so you can't really set a numerical target on that per se, although some people do have software reliability. There are different approaches to that, but usually we look at the software assurance rigor level. DO-178C, which is the software safety standard for the aviation, and they have, again, different development levels vary according to the risk of that software. And again, DoD, our approach there is that excuse me, each software function has to be designed, coded, tested, and verified according to the level of rigor that is set. Levels of dependability, as I mentioned, is just a term that, and you'll see these specifications for almost any system, has a certain reliability number, availability number, safety. We don't, we have, as I mentioned, different assurance levels. And then cybersecurity, we're just struggling with, at least in Department of Defense, as to all the things that have to be done for cybersecurity. Design time assurance is basically the analysis and testing of your product, of your software during development. If you can fully V&V your software during development, then you can consider that, quote, trusted software. Now, if you can't, or for that software you can't completely V&V, and that is not completely trusted, then the recommendation is you do runtime assurance, which is basically, that's my untrusted software. I couldn't completely verify and validate, so at runtime, we do things to make sure that it's operating correctly every time it is ready for live operation, so to speak. And then, and I think this was mentioned, in fact, I know it was mentioned a little bit before, which is, so your runtime monitoring will detect anomalies or failures in your autonomous systems, and it'll go to a reversionary system. Usually that is something of a less capable nature. And so, for example, a UAV, your monitor, or your runtime assurance rather, would revert to a less capable function, say like a return to base. And there was some mention about the drones we have now do have a return to base capability. The current processes we now have, and I won't go over this much, for aviation, the FAA, their position is that current safety critical flight systems are, quote, trusted by the public and the regulators because they meet their rigorous criteria of certification criteria, and there are various standards for that. In this case, DO 254 and 178 instills adequate trust in unproven complex software systems, and this is right now what they're trying to do, apply to automation or UAVs. And again, the UAVs are going to have to be, unless the regulations change, they're going to have to be certified the same way that a manned system is. And this is very difficult because, again, there's no fallback option for a pilot when we are into UAVs. Just a little bit about the automotive business. 26262 is the main certification standard now. In Europe, it's required, and they add on, again, they have ASILs, automotive safety integrity levels, and they add on a level of controllability by the driver. For the US, There is no requirement for certification. The NHTSA, the National Highway Traffic Safety Administration, as is often the case in the United States, they say you have to meet certain standards, but you, the manufacturer, can determine how to do that. Unlike the Europeans who say, 26262 is your only choice. In the US, you have different ways. You just have to meet, in this case, you have to show that your vehicle meets federal motor vehicle safety standards. And so the developer or the manufacturer is allowed to, quote, self-certify. In most cases, though, and Ford, when I was there, was an example, is everybody, all the US manufacturers are trying to go through the 26262 process as part of their certification. So what are the solutions? We've talked about you have to have verification and validation of an autonomous system. It's difficult because requirements are difficult to develop. You have an unlimited state space, permutations, combinations of testing. You might have emergent behavior that occurs because of either machine learning or combinations of different systems interacting. So the proposed solutions essentially is fourfold. I mean, there are a number of solutions. What we've concluded and are attempting to do is address it by addressing requirements complexity, by the architecture itself, by new test and verification strategies, and by going to a safety assurance and with a nod to our British friends, to a safety case approach, which we don't necessarily do that often in the US, but it does seem to be appropriate in this strategy. So for autonomy requirements complexity, there are several solutions. Break down the requirements into smaller pieces that you can make into more of a quantifiable, statistically, a design that you can show statistically that you meet. You can also do, as I mentioned, functional safety specs at the time. You gear these toward your runtime assurance. You can define safety-specific requirements for your system that are different than your functional, not to mix the two, but definitely design, what is a safe system? And those are the requirements you absolutely have to meet. And then from there, you can be a little more flexible in how you meet your other requirements. And then one of the architectural approaches is what they call, and this was mentioned already, is a monitor actuator concept. This is very much the recommended solution for most of the literature right now, which is to have a actuator system being your functional autonomy, and then your monitor system is a safety critical or a high ASIL monitor, high safety integrity monitor that will monitor the operation of the autonomy, and if there's an anomaly or failure, revert back to a less capable safe system. And the next slide talks about that as far as the architecture itself. You can find this in the literature. This is a runtime assurance protected system, and it talks about the advanced system, the autonomy being, quote, untrusted because you can't verify and validate it completely. The monitor, the runtime assurance monitor, would be safety critical. You would have all the features for a safety critical system, such as partitioning, bounding, all the software safety aspects, and the redundancy, diversity, data integrity. And then there would be runtime assurance, which would be, again, fail operational or fallback with limited functionality. As far as test verification and validation strategies, there's more emphasis to use more formal methods to try to prove the absence of faults. Instead of trying to prove that something works, try to inject faults to make sure, or as a safety argument approach, that trying to invalidate your safety argument, so to speak. Simulation, again, as much as possible. probabilistic results and risk assessment versus trying to come up with numerical targets. Again, test and simulation throughout the life of the system instead of that V model of systems engineering I showed, where you do your development along the left leg and then your V and V along the right. It's recommended you start verifying, validating every step of the way as you start building basically your safety case. And then again, test to ensure unaccepted behavior will not arise at runtime. Phased introduction, which is introducing autonomy gradually. This is what the automotive manufacturers are doing, starting with no autonomy, limited autonomy before you go to full autonomy. And we are still, I was in Phoenix some few months ago where they do have actually some autonomous taxis are in operation now, but that they're using very limited environments where they know the environment. Arizona is a nice environment for the radar and LiDAR, and so they're doing it in a safe environment as much as possible, and that's of course the right way to do it. And again, excuse me, and again, fault injection, which is try to inject faults, falsify your claims of safety, and also test for robustness. And, for example, you would insert invalid maps into data, not necessarily a safety feature other than the fact that, way back when you first had your GPS guidance system in cars, every now and then someone would follow a GPS and run their car into a lake or something because they followed it without thinking. So anyway, to do that type of scenario fault injection. And then use a safety argument approach or an argument-based assurance. Because of the complexity of the autonomy, the difficulty in establishing full requirements and 100% testing, that the proposition is that we create a safety assurance argument. Use evidence-based approach. With a safety case, you make claims and assumptions and then use arguments and, for example, formal methods to buttress your argument or provide evidence. And again, one of the concepts that's been recommended and accepted is the use of a fault detection monitor, the actuator monitor approach, where your monitor is of the high SIL value and your regular functionality is not. And then on the aviation side, again, do a good software safety requirements you're already required to comply with, for example, DO 178C, and that is conducive to providing evidence of a safety case. The FAA, probably more than most, looks at a safety case approach to these. And again, just on a safety case, comprises both a product-based argument and process-based arguments. One of the advantages of the safety case approach, at least theoretically, is that you can establish building blocks as you develop your system so that what you've done builds upon previous work, previous testing, and you can continue to compile evidence, a body of evidence. Now, one of the difficulties, particularly in machine learning, is, and this was kind of alluded to in the previous presentations, when they find a system defect in your system and you have to make a change, does that not invalidate all your previous testing? I mean, it can, traditionally. So you have to try to figure out how, when you're gonna find defects and make changes, how to kind of maintain the credibility or coherence of your safety argument and not have to do a complete rerun. Because again, it's a matter of trust. If I've found an error in my autonomous system and it's killed somebody, now, do you trust all the rest of my autonomous functions? I don't know. You have to think about those things. There are a number of examples of safety cases out there for automobiles. One of them that I was looking at It starts with a safety target or safety integrity level like an ASIL. So you have safety targets to go for allowable or tolerable failure rates. You build up evidence through your study analysis, test, and evaluation. You present those with, you can either use a fault tree approach, which is more common in the US, or a goal-structured notation approach, which I'm learning to like more than I used to. And then you provide context, of course, as to your argument. So really in conclusion, and again, it's very difficult to do verification and validation on complex software systems, which are non-deterministic, meaning you can't really predict what they're going to do. The environments are complex. The decision state space is almost infinite. And you might get unwanted emergent behavior. Very difficult, and right now we don't have a good way to do it, to instill trust in our government regulators, and we're working with them to do this. But we have maritime systems. I'm working on an autonomous submarine, and we of course have UAVs, and as we continue on, our government is asking us, how are you going to give us trust in you? And this is what we're struggling with right now. We know that we can't do 100% testing. We can test as much as possible, but we have to use simulation as much as possible, and other forms. Certification is a challenge. And then, so for developing a trusted system, we're going to, again, try the established safety targets, so we can do this. Software assurance, including runtime and design time assurance. High dependability, we can hit numerical targets on reliability and availability. Cybersecurity, we're still working on that. There are architectural approaches and formal methods and fault injection on the testing side. And again, the safety case approach, which I think the US government is becoming more open to that type of an assurance approach, by virtue of the fact that we cannot tell them, we absolutely will not have an incident or a failure or a crash. We can give you a probabilistic assessment. We can give you evidence that this is the case. We could build, and this is where my legal background helps a little bit, a safety case is much like a legal case. You're building evidence, you're building assurance, you're building confidence, so at the end of the day, more likely than not, you're going to accept this product. And that's currently the approach we're taking, and it is a work in process. I think that's all I have. If there's any questions.